And the resistance in here, we can make it like 89. Make this like 10K over there. 4 kilo. 4 kilo. I think it's all set. Gate, drain, that's the source. So this is a variation of collector feedback. Yes, sir.
Do we have the value for RC?
Yes, in a minute I'll give you the value for that one. RC is also equal to, let's say, 2K close to a saturation point, 3K. Maybe RC equal to 3K. Okay, let me erase this. It's all set. Beta is 100. For the FET, this is the information that is available. Kn value is 100 milliamp per volt squared, and VTH is equal to 1.5 volt. Okay? So problem is all set. We have to see what is that. This is going to be a common source amplifier, CS, actually, obviously, because S is literally grounded, not just by a capacitor, but straight goes to the ground. Common source amplifier, and there is a capacitor showing up in here. You may wonder what it is for. The purpose of that capacitor is to stop the feedback from the collector of that transistor going back to the input. If it wasn't there, as the input rises here, input rises, the drain voltage will tend to go down, opposing the rising voltage in here, and it would reduce the actual input. It will lead to loss of voltage gain in this circuit. So this CS amplifier would not provide the same voltage gain that it will provide with the CP, because there will be a feedback, local feedback in here. We're not going to go into the feedback. Or if you want, remove that capacitor and reassess the voltage gain of that stage with the effect of the feedback in your AC model. You can do that. But that's not the intention. In here, we want a full common source voltage gain out of that stage number 1. So how do we kill that feedback or bypass the feedback? This is the answer. If you put a large capacitor here, large enough, this capacitor will be a short circuit. Once it short circuits, it will short that point to the ground. So when you're applying an input signal here and the output changes, the signal will not return back to this input, because it will be shorted straight to the ground. From this point, it will be shorted to the ground, AC-wise speaking. So this is for grounding that point under the AC. So the amplifier will turn into a common source amplifier, simple common source amplifier. We will draw the equivalent circuit later when we do the AC analysis. But first thing is, number 1, DC analysis. How do we go about analyzing the DC in here? Okay, so how do we do that? For DC analysis, this is done stage by stage. Because the capacitor is there, you put the capacitors to open, this one to open, that one to open, you recognize what is that one. This is the good old CE amplifier, straight CE amplifier. We will do the DC analysis of that one, then we will perform the DC analysis of this one. Again, you put the cap to open, this one to open, you will look at the DC feedback which comes in, and it will come in, the DC feedback. This will not help to stop the DC feedback because it's open circuit. Under the DC analysis, you have nothing here. It's just an open. So which one shall we start with? And we have a mathematical equation for the FET. So this is the equation for the FET, which we can use to algebraically solve all the quiescent voltages and the currents in that stage. So DC analysis, stage 1. So this is stage number 1. And that is stage number 2. DC analysis. Stage number 1. So let's draw that separately. Here. Here. You have 4K. You have 400K here. Another 400K that goes in series with it. So effectively it's like 800K going to the gate. And this is the FET, drain, gate node, source node, straight to the ground, and that supply is 18 volt power supply. So find ID, VDS, and GM. That's the first requirement here. Oh, sorry, we forgot this one as well. 200K. 200K. So from that reduced circuit, simplified circuit, because capacitors don't count, this capacitor doesn't count, this comes out. So calculating the currents. Let's see. Let this be ID. Let that be ID. Okay, there is a very easy way to calculate that. I'll tell you why. 18 volt over here, we have 4K over here. Let's examine that, just by expectation. What do we expect? What do you expect the voltage to come out of here? 200 volt? Do you think this voltage can be 200 volt? Minus 60 volt? Don't you expect it to be somewhere between 0 and 18? Yeah. That's a reasonable thing. Let's say it goes in the middle, right? It's just in the air. Take, it is 9 volt, not 10 volt, okay? Some 10 volt. Then what will be the current in this path?
Very small.
10 volt divided by 400, that's a 1 mega. 10 microamp, okay? So that assumed 10 volt, we're going to cross this out in a minute. This is going to be like 10 microamp. Agreed? Okay, what will be the current in that resistor? With that 10 volt. 18 volt, 10 volt, there's 8 volt dropping on that. 8 divided by 4, 2 milliamp. 2 milliamp is 2000 microamp, right? I'm going to write the nodal equation at that point, at this point, nodal equation. You learn that according to the number of the branches, you take voltage of that node minus the other one and the other one and the other one, you divide by the resistances, right? But look at here. If I take this voltage minus that voltage divided by 4K, I'll get something like 2000 milliamp. But if I take that voltage, 10 volt, minus the node voltage in here, of course, recall that IGs are 0 in the FET. IG, DC IG is unconditionally 0 in an FET. So this 10 minus voltage over there divided by 400 is going to be a very, very small voltage in comparison to the 2000 micron. Next, with a 10 volt over here, you're going to have, this is 2 over 800. This is like 1/10 of 10, actually, sorry, 1/5 of the 10, which is about 2 volt. It is greater than the threshold voltage, so we are going to see a significant milliamps in here as well, in the drain current. Out of the 3 currents, you notice that this one is the smallest, all right? So we are going to take it to our convenience and completely ignore it, as if that current is ignored. Ignore current in the 400 plus 400 plus 200K resistors. This is a reasonable assumption. Remember, you're ignoring compared to what? This is your reference. That it is something in the order of milliamps. We know that. Because voltage can be maybe 5 volt, maybe 15 volt, but it is in the milliamps compared to the 10 micron. So it's a reasonable assumption. See how easy then the calculation will be. You will have, call it V of the D. Call that current ID. So node equation at D, at the drain, ignoring I of the 400, 200K, ignoring, because that's a series assembly of resistors. We're ignoring that current. So let's see what will come out of it. Node equation. You will have ID, current going this way to the drain, plus V of the D, voltage of the D, minus 18 divided by 4K equal to 0. Equation 1. Equation number 1, okay? So let us organize that. Okay, we can do it one step later. Now, incorporate these equations. Transistor equation. Assume transistor that is fed is in saturation region, i.e. V of the drain to source is greater or equal to VGS minus VTH. That's the condition for transistor being in the saturation. Now, transistor equation. Equation in saturation. I of the D is equal to Kn over 2 VGS minus VTH squared. This will be your relationship between gate to source voltage and the drain current. So we substitute the values. It's given in the milliamp per volt squared, stick to it. Milliamp volt squared, volt, kilo ohms, we keep everything in that scale. So we will have ID equal to 50 multiplied by VGS minus 1.5 squared. Equation 1, equation 2. So you have now two equations, 200. ID VD and then ID VGS, but there is a link between VD and the VGS. What does that mean? If this node voltage with respect to ground is VD, then this makes a voltage divider. You can see 200, 400, 400. It divides that voltage. So we can say VGS is also equal to 200K divided by 400 plus 400, like series, plus 200, multiplying by V of the D. So is equal to, that's 200 over 1000. They're all K's. So multiplied by VD, that will be 0.2 VD. Effectively, this is our kind of third equation. You can say it's a third equation. So we make a straight substitution from 3 into equation number 2, and let's see what we will get out of it. Substitute VGS into 2 from 3. From 3. So here we are. We get ID is equal to 50 times 0.2 VD minus 1.5 minus 1.5 squared. So we can call that still equation number 2. Okay? So what we have is ID equal to that, and ID plus VD is equal to this. So we will eliminate, for example, ID between the two. Eliminate ID between 2 and 1. Okay, so we will get here 18 minus VD over 4 is equal to 50 times 0.2 VD minus 1.5 squared. That's a quadratic in VD. You should be able to solve that. Okay, so let's see what will be the answer to that one. We can multiply by 4, so it will be like 18 minus VD. 4 times 50, that's 200. Multiplied by 0.2 VD minus 1.5 squared. Okay, so 18 minus VD is 200 times 0.2 VD squared. That will be 0.04 VD squared. Twice of 0.2 times 1.5. That will be 0.4 times 1.5. 6.6, yes, 0.6 minus 0.6 VD and plus 2.25, that is 1.5 squared. So this will come out of it. Let me check and make sure. That's 0.04, yes.
Are we not missing like a negative number? Because you moved ID from the other side.
I multiplied that, that's good. 0.2 squared, it is 0.04. 1.5 squared, this one.
When you move the ID to the other side, should it be negative?
Let me check. ID is, I already did.
Oh, yeah. I don't know.
It's done, yeah, because I flipped the direction.
Yeah.
That's done already. Okay. Oh, thanks for following me, you know, because, I don't wanna make mistake, but you know, never know. So 0.04 times that, twice of that times 0.4. Yeah, 0.6 times VD, yeah, it's covered. Now we distribute that 200, which is going to make it a little prettier. So these two shift, we get 8 VD squared. And then 200 times 0.6 shifts there, and then 20, it will be minus 120, but we got the VD in here, so it will be minus 199 VD. Yeah, I think that's correct. Let me check again. Minus 120, yes. Minus 120 and a 1 is minus 129. So 120, or 19. It's bad. Okay, we got that. And then, so this is figured out. Now the 18 numbers. 200 times 2.25, 2 times 2.25 is 4.5. 450, 450 less 18. 450 minus of 18. 432. Equal to 0. Okay. See if it is correct. You do the checking, 0 shift.
Yeah, you got the same.
25, that's 450. 450, 18 goes there, subtracts. That's correct. This equation is correct. Let's throw it into the calculator and get the value of the VD. So it's 119 plus and minus radical 119 squared minus 4 times of 8 multiplied by 432 divided by 2 times of 8. Okay, so finally we got an answer. Let's see what is that. Now calculator. 119 squared minus 4 times 8 times 4, 32 equal square root that equal. So this number turns to be 18.35. So two answers will come out of it. So we've got to decide which one it is. We'll take both of them and examine them. So one of them is 18.36. 18.36 plus 119 divided by 60 equal to here 8.58. 58 and 5 volt. This is one of the answers. We've got to check which one is valid. Then a second one, VD, first, second, is 119. Was that the plus I took or the minus?
6.29.
I took minus?
6.29.
6.29, this one? Okay, good, thank you. 6.29 of a volt, all right? Having figured this, you take the VD into calculating the VGS. That's the trick. So remember what was the link between VD and the VGS? Right? What was the link? 0.2 times,
Yeah.
remember? So if you take this answer as the real solution, it's going to be 0.2 times that. So 8.2 585 multiplied by 0.2. This will be the answer. VGS will equal to 1.717 volt. Try the second one. VGS will be equal to 0.2 times 6.29. 1.25 volt. Okay. Tell me, which one is acceptable, which one is not?
The top one, because mine is 1.5 and it's still positive. The other one, minus 1.5 was negative, which is unacceptable.
This is under the threshold. See? This is less than the threshold. Less than the threshold, ID is automatically 0. It doesn't even exist because the actual curve, this equation, is only valid if VGS is greater or equal to VTH. Otherwise, that equation, you know what, is equal to 0 if VTH is less than VTH. VGS is less than VTH. So this is not valid solution. That one and this one, because of that. So the answer to this problem will be, therefore, VD, which is same as VDS, will be equal to 1.717 volt, and VGS will be equal to, sorry, VD, not that. VD is equal to 8.585 volt, of course. VGS is equal to 1.717 volt. And if we want to check to see if VDS is greater or equal to VGS minus VTH, to validate that it is in saturation, this is the saturation condition, sat condition, then check here. Is 8.58 greater than 1.71 minus 1.5 volt? Yes, it's validated. 8.5 compared to 0.2. That's what it is. This side is 0.2 because that was the condition. This is the condition for stating that equation. Otherwise, this equation wouldn't be valid. You're assuming VDS is greater than VGS minus VTH. You need to validate that in the end with this data. Yes, so we've got that as a complete answer. Transistor is in saturation, operating in the saturation region, which is the useful region. And ID, then what's ID? That's straightforward. Therefore, ID will be equal to, we make a substitution over there. I won't write the equation for it, it's just straightforward. 8.58, 8.585 minus that times 0.2 times 0.2 is equal to that minus 1.5 squared times a 50 here. ID is 1.232 milliamp. You get 1.232 milliamp. Let's see if it makes sense, okay? Do I have here, do I have 1.232 milliamp going down? Something is fishy here.
I got 2.32.
You got 2.2?
Or I got 2.35.
2.25 milliamp.
2.35.
Yeah.
2.35
You can just sub it into equation one.
You substituted in, I substituted in equation 2, you substituted
Yeah,
the
equation one.
equation 1. Okay. So this is the value. 2 point, say 2 point again,
2.35.
2.35, 2.35 million. Yes, because immediately I got the feel this is not right. That's too low for the current. So current there is 2.35 milliamp. Okay, what's the voltage on the 4K? That multiplied by that, V of the 4K is equal to 4 times that. 2.35 times 4, 9.4 volt. So V of the D is 18 minus 9.4. 18 minus 9.4. Plus 18. 8.6 volt. Look at that. 8.6 volt agrees with what we got over here. VD 8.6 volt. Okay, so we're okay. It's useful to do such a check, because even no matter what we do, mistakes are possible. So this is done. We collected the data. We know it is in the saturation. One thing needs to come out of it before I start building a small signal equivalent circuit, and that is the GM. GM, the small signal transconductance, small signal transconductance is equal to radical to Kn ID quiescent. So this will reveal the value of the GM that that transistor produces. We get 2.35 exponent minus 3 multiplied by that 0.2 amp per volt squared multiplied by 2 square rooted. There it is. GM is equal to 1 decimal point, another 0.0307. S, it's in Siemens. Yeah. 0.03, that's correct. So this is the GM that we have from that transistor. You keep it there, you check that it is, yes, it is in the saturation with the current, and let us start with the second one. Okay, if you want to take a picture of that one, please take it, because I'm going to need space. The second one is almost as much. Yeah, from the left and the right, because there's a